All right, so in this video, we're going to be looking at non-parametric hypothesis testing, so particularly the Wilcoxon test, and we're also going to be looking at Friedman's ANOVA. So let's go ahead and get going. We're going to start by entering our data as a vector. So we've got some raw data. Now, the rank sum tests in particular, they give us a little bit more flexibility in terms of what we can conduct our hypothesis tests on. These tests do not generally require an assumption of normality, typically only things like symmetry or something like that. So they're a little bit less specific in terms of the kind of data that we can use. And they also allow us to test things like the median rather than just the mean. The median is one of those things that you typically have to simulate or do bootstrapping on in order to construct confidence intervals and that sort of thing. So doing a Wilcoxon test, a non-parametric test, gives us the power to do stuff like that without having to do that kind of simulation. 505.8. Now let's just try and get all of this on the screen so we can see it all and make sure that I haven't left anything out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yep, 15. Okay, hopefully I haven't made any typos along the way. Let's go for it. And then we're going to conduct the Wilcox test on our x variable. And what we want to know in this example is we want to know if the difference between this data and 500, if there's a difference between this data and the mean of 500. So mu here in the Wilcox test is essentially the null hypothesis that we're comparing to. Now, the Wilcox test is essentially a rank test. So what you would do is you would rank all of the things, and then you would subtract off the 500 that you're comparing it to, and then you would look at the signs of the different ranks, and you would add those up, and that would give you some information about the behavior of the variable, because basically it's going to compare it against 0. You should have equal numbers on each side, ideally. So let's go ahead and run this. And what we get is a p-value of 0.1688. So the alternative hypothesis not equal to 500 indicates that this is too high to reject the null hypothesis. And so that would suggest that our data does in fact appear to have a mean of around 500. Now, we can also do this with a 2-variable example. So let's take some new data. So we have 2 variables, and we can conduct a paired or unpaired test with 2 variables. Now, like the t-test, when we do paired data, what will actually happen is the test will calculate the difference and then conduct a one-way test on the differences. If there is a two-way test, then you're going to conduct a slightly different test called the rank sum test in this case. So let's double check to make sure I have the right number of variables in each case, 10 and 10, that's good. Obviously, if they're not the same length, you can't do a paired test. But if they're different lengths, then that's no problem for the unpaired test. So Wilcox.test is the same test, even though the calculation is a little different. When we specify two variables, then we can add paired equals false to do the rank sum test and paired equals true to essentially do the differences and then the one-way test that we did before. So if I run this, again, it's going to calculate, there's a test statistic W that goes with these Wilcoxon tests. For certain kinds of sample sizes, you can treat this kind of like a normal distribution to calculate the p-value, but there are formulas for calculating the exact value of the probabilities associated with W. But in this case, we get the p-value calculated for us, which is 0.02. The null hypothesis is that the two have this essentially the same value. So the difference between the means is 0. In this case, the alternative is that it's not equal to 0. And so this would indicate that it is true that they're not equal to 0, that there is sufficient evidence to make that conclusion. Now, there are some different ways to do ANOVAs in a non-parametric way, or the equivalent of ANOVAs. And one of these is called the Kruskal-Wallis rank sum test, which is somewhat similar to the idea behind the Wilcox test, but now it's going to be a little bit more involved because there's more than two variables involved. So again, we're going to bring in our MT-CARS data that we were using for the regular ANOVA, and we are going to convert one of our variables to a factor. We're going to do cylinder again. There we go. And then the test is called Kruskal.test. And again, this syntax works similarly to the ANOVA. We're going to model MPG based on our factor cylinders, and we're going to extract our data from the MT-CARS data set. And when we run this without saving it to a variable, it will just print the results directly to the screen. And we can see that the p-value is also quite small. So this analysis actually is similar in terms of its interpretation to the one-way ANOVA that we did in the previous video. This p-value is quite low. That indicates that there is at least one mean that is different from the others compared to each other. So at least the 4-cylinder is different from the 6-cylinder, or the 4-cylinder is different from the 8, or the 6 is different from the 8. At least one of those groups is different from the others. And we saw actually previously that they're all different from each other in a statistically significant way. Now, once we've determined that there is a difference, then we want to find out, well, again, which of the levels are different from each other. In the regular ANOVA, where we were assuming normal distributions and all those things, equal variance and everything, in the Kruskal test, we don't have the Tukey method available, but we can do a pairwise Wilcox test. And we said in the previous video that if you're doing traditional ANOVA, instead of doing Tukey, what you can do are pairwise t-tests. But in the non-parametric case, we have a pairwise Wilcox test already set up for us. Now, here we're going to have to specify the vectors, MT-CARS, MPG, not the data set, and MT-CARS and cylinder are two variables. And then we have, because we're doing multiple tests, it's common in statistics to adjust the p-value to account for the fact that you are doing multiple tests so that the combination of them is still like 0.05 or whatever, rather than individual tests being 0.05. If you do multiple tests, then that 0.05 actually is going to be quite much higher because each time you do the test, you're saying it should be 0.05. And so in this case, they're actually going to make an adjustment to account for the fact that we're doing multiple tests. And because there are three cylinder levels, we have to account for the fact that we're going to have to conduct three pairwise tests simultaneously. So we can run this. And again, there are different methods for doing this adjustment, but this is one of them. And we can see, we get a little bit of a warning message, but don't worry about it. Here, we're looking at the outcomes of the variables and the p-values for each of the different pairs of variables. Now, this is displayed a little bit differently than in the traditional ANOVA, but we interpret this table as this is the p-value right here for the difference between the 6 and the 4 cylinder levels. Obviously, there is no difference between 6 and 6. This is the difference between 4 and 8 cylinder levels. And then this is the difference between between 6 and 8. That's how we would read this table. So we don't get the actual like confidence intervals like we did with the Tukey, but we do get the p-values so that we can tell again whether these combinations, these factor levels are different from each other. If the individual p-values are above our significance level, then we would say we fail to reject the null that they're the same. And if they're lower than our significance level, then we would say we can safely reject the null that they are in fact different. Now, we can actually also conduct some additional kinds of data, such as Friedman's ANOVA. Now, Friedman's ANOVA requires data of a particular type. So typically, this is sort of like a paired type of test where you are measuring things at different points in time on the same observers, for instance. So maybe you're giving somebody a sample test and then you're giving them some training and then you're testing them again and then maybe you're training them some more and then you're testing them again, or you're giving them some medication, you're testing them at different points of time at the same person at different levels or after a certain amount of time has passed. And so there's a relationship between the individual observations in each of the categories. Now, the empty cars data set doesn't satisfy that kind of a condition. And so for our example, we're going to enter some data and create a data frame for it that does meet those conditions. Data.frame. And so we're going to have some people that we're going to call 1 through 5. And their individual observations, that's going to be our first column of data. And then we're going to have the drug levels. And then we're going to have their score. And so we're going to run that. And here's our data. We have 20 observations of 3 variables. So it looks like I didn't miss anything because 4 times 5, that should work. And then we're going to conduct our Friedman's test. So the numerical variable that we're modeling is the score. And then the groups are going to be data, the drug column of the data. And then the blocks are going to be those individual people that were repeatedly being assessed under each of these conditions. So each of the 5 people is receiving each of the 4 drugs, and then the score variable is their response to that analysis. Now, for this kind of a test, you do have to have a data set that is specifically designed with this kind of analysis in mind. So it's not just a general two-way ANOVA. This is some sort of a paired type of thing. And again, the outcome that we get when we don't save it to a variable is that it does give us, it's doing its analysis based on a chi-square distribution, but it gives us the p-value, which is what allows us to make the assessment of the analysis. And this would indicate that for this particular type of paired two-way ANOVA, that the p-value is below the typical significance threshold. And so that would indicate that the behavior for this data, that it does differ by person and by the drug or the drug level, whatever these 1, 2, 3, 4s represent.